All right. Good afternoon. My name is Wayne Menning with Ohio Concrete. I'd like to welcome you on behalf of the association and specifically the promotion directors, Bob Krulik, Lisa Weaver, Moon, and Joe Vogel, and myself. Thanks for coming back after the long break and through Thanksgiving. Hope everybody had a good holiday. I do want to remind you of a few things. Please put your questions as Dan is presenting in the Q&A box and try and not use the chat box. We prefer that. And also, if you do need to get off before we end here today, I want to remind you that next week it is a Tuesday webinar. So change in scheduling. These last two next week and the week after will be on Tuesday, the 8th and the 15th, same 1:30 to 2:30 time slot. Okay, so without further ado, I'm going to go ahead and let Mr. Dan DeGraaf with Michigan Concrete Association, their Executive Director, CEO, go ahead and get started on his presentation on the 30 and 50-year pavement designs. Dan, thanks for being here, and it's all yours.
Thank you. Thank you very much. I've had the pleasure of attending OTEC a few times. So I am familiar, and my son is a graduate of the University of Cincinnati. So I spent many days traveling back and forth through your great state of Ohio. And so I got to review your roads. A little bit on just quickly on my background. I graduated from Michigan Tech, and I spent about 25 years as a contractor building highways and roads and airports all over the United States, some time in Michigan, quite a bit of time in Colorado and Texas, Indiana. And I came back home to Michigan to work for the association back in 2000. So, but I've had the pleasure of working in many different states and watched how people do things differently in other areas. But a few years ago here in Michigan, we went on an endeavor to build a 30 and a 50-year pavement. And I'll get into a little bit of the definition of that here in a minute. But as with all good ideas, it started somewhere. In our case, road funding issues brought this to the forefront. All road funding dollars come from the legislature, who have limited terms. So they look on a short-term horizon, whereas the DOT is responsible for the health of the entire network over the long term. And there's always a little bit of a disconnect there when you try to communicate. But funding is an annual battle. The other thing I've noticed, and it's in my seat, is that there are new miracle products that are brought on the market every year. And a lot of times people promoting products like this have found the legislature to be a good place to get some traction on their new ideas. And so they come to the legislature as well as the DOT. And as they paint the picture, the legislatures get the impression that the DOT is very inefficient. They don't grasp on to new things. And so they keep talking about efficiencies. If we could just make the department more efficient, we wouldn't have to come up with new money. We could just fund the roads with efficiencies. So that's kind of the ground rules where this all started. So back in 2015, the legislature agreed to, over a 6-year period, increase the road funding in Michigan by about $1.2 billion. But that came with a hook, and that was that the department was required to set up a road innovation task force. And their task was to evaluate materials and methods that could allow for roads to last for 50 or more years. They were willing to spend money up front as long as it produced life cycle cost savings over the long run. They wanted to focus on longer term fixes to maximize the value. They were going to monitor and track the progress. And they also had a caveat that a significant chunk, like $100 million of funding, was going to be tied up until this task force investigated, reported, and had a plan to proceed. We talk about what are we looking at? Currently, the department, their standard design is based on a 20-year design using either ASTRO 93 or the ME pavement design. But we look at 20 years of traffic, 20 years of performance. But they've historically found that with that 20-year design and maintenance, they can typically get a 35-year service life out of a pavement. So the proposal was to come up with a 50-year design, which would project maybe 75 years of service. And as a sideline to that, they said, well, let's try a 30-year as well. So what was established back in 2016 is they elected to build 4 projects, 2 in asphalt and 2 in concrete. Each one was going to have a 30-year design and a 50-year design. And I'm going to basically just talk about the concrete ones. When you look at cost, the standard design for this one section on our project in Grand Rapids, about $1.4 million per lane mile is what they were going to spend, with an equivalent uniform annual cost over a 35-year life of $55,000 a year per lane mile. The 30-year design and the 50-year design, 30-year design cost about 10% more, and the 50-year design cost about 15% more. But as you can see on the far right side, the equivalent uniform annual cost for the 50-year design was down at $37,000, which is a 50% reduction in the uniform annual cost. So the concept is there. If we spend the money up front, we can get better bang for our buck long term. At least that was that's the theory that we've operated under. Obviously, it takes more money long term. Initially, we're going to have a bigger amount of funding that could taper off in the future years. But is 75 years really possible? And we had a chance to go down to Bell Fountain a few years back. That was a piece of pavement built in 1893. You know, it's 127 years old now. So it is possible to build long-term. In Michigan, we have several great examples. One is between Holland and Grand Haven, a piece of pavement that I remember as a young kid, that it was, when we crossed the 4 lanes of concrete, we were almost to Grandma's cottage, and my trip was almost done. But that project is now 66 years old, and it's still being used today as a concrete pavement with a concrete surface. US 131, if you've been through Grand Rapids, that was built in 1958, and we're still driving on much of that as original surface. It has been repaired, CPR'd a few times, and diamond ground at least twice now, but it's still carrying on. And then over in the Flint area, in an area that has more clay soils, we still have one that's now 53 years old that's going to be rebuilt next year. But and then we also have many, many miles of composite pavements all over the state where the base pavement is still carrying the load, even though it's been covered up with asphalt. But what we did find is well-drained pavements tend to perform well. So as I drive and I travel, I look at pavements, and many of you are pavement engineers as well. And you know, your wife always tells you, why are you looking down all the time? Well, we like to look at the road we're driving on. We like to see what's happening. But as I look at progressions over 18 or 20 years, a lot of times projects are 10, 15, 20 years old, and you don't see much going on with them. They're just there. If we do have a problem with durability, that usually shows up in year 5 to 10. And we'll talk about some things we've done that I think we've solved some of those problems. But you're going to find that at some point you're going to start feeling a little bit of faulting. And and it usually starts in the truck lane. And so that right lane gets a little bit worse, but the passing lanes are always pretty good shape. We see a sealant breakdown, we got edge loading, cracks start to form. And then we see some of the panels start to move around a little bit. Maybe you see some more spalling going on. But the pavement starts to move as the repair seasons start. And that's what I see for a couple of cycles of patching usually happen. You know, every 7 to 8 years, you'll go in and do some patching, diamond grinding. And then around year 35 is where on average we turn it into a composite or talk about reconstruction. But we have many examples of pavements that are still left in service long after that because of funding is always a problem. So what do we need? I have seen very few pavements fail because they're really not strong enough or thick enough. But they seem to reach a point where the base support starts to let the pavement surface down. And then we start seeing failures. And you get to the 40 to 50-year-old concrete, you start seeing the surface start degrading and the surface starts crumbling. So it goes hand in hand, but water seems to be our common enemy. The subgrades are affected by the water and the moisture, as well as the freeze thaw and the durability of the surface of the concrete. So what do we need? We need a longer lasting subgrade support. This is our real issue that we've got to work on. And like I said before, durable concrete has been an issue, and we are making some really good progress on the durability of our concrete. So the committee came back from their looking and researching. They went off and the committee was actually an internal task force of MDOT staff. They did reach out to industry. They reached out to academia. They inquired from other DOTs around the country for input. But they were on a very short timeline and tried to pull some things together in a quick order. The one thing they came back with is for the better long-term support, maybe increase the granular thickness area. In Michigan, we built almost all of our freeway sections with a 10 to 12 inch layer of sand underneath them. And I'll show you that in a few minutes. We want to increase the drainage. And they decided that a 2 to 3 foot freeboard from the under drain to the ditch bottom was going to be something they were going to require of this upgraded piece of pavement. They wanted to stabilize the aggregate base layer that was placed directly beneath the concrete layer. They really liked what they've done with some of these stabilized bases, and they said, we're going to add that to the system. And then the other thing we talked about, and I know Ohio, you've got a lot of experience, but our talk was about waterproofing the subgrade with a soil stabilization layer, to stabilize that top layer of the existing subgrade soils. And that is to keep that grade in the same condition, support condition, for a longer period of time. If we have an MR of 3,000 or 4,000, we want that MR to be there still at that 3,000 to 4,000 level in 25 years. We don't want the top of that subgrade to deteriorate because it got saturated and we lose that support on the top few inches of that clay grade. What I'm showing you here is our 50-year sections. We actually built 2 50-year sections. The far left, this is our standard 20-year design. We have existing grade. We bring in this case now we've reused it. It's 10.5 inches of sand subbase. That's a class 2 type material. We now throw a geotextile separator layer over the top of that. Usually this is a woven geotextile. And then we place 6 inches of open graded aggregate on top of that. And I have, over the years, what does 6 inches of open graded really mean? In Indiana, we built with 4 inches of open graded material, but it was basically concrete aggregate with no sand. So it was very marbly. You couldn't hardly walk on it. When the open graded we have here in Michigan, the 6-inch open graded layer is built with a well graded, larger size or 3/4 down material, but we limit the -200s. So it's a material that you can drive a pickup, you can drive a truck on. You don't want to use it for a haul road, but you can back a truck in front of a paver and dump concrete on the ground on this surface. It will hold that, but it allows that water to go through, but it also has enough stability that you can actually walk around and do things on it. And then on top of that, the design for the 20-year traffic counted for a 10.5-inch concrete pavement section. When we went to the recommendation, now we've added 20 inches of sand, same geotextile layer, 6 inches of open graded drainage, the same material that we put under our standard pavements. And then they put another 6 inches of cement treated open graded material. This stuff gets to about 1,000 PSI in 7 days. And then on the top of that, 10.5 inches of concrete again. That's a 42-inch section versus our old 26.5-inch section. We'll keep that in mind as we go forward here. We also did another twist on this project, is we used a 12-inch subgrade stabilization and reduced the sand subbase to 8 inches, 6 inches of a dense graded aggregate, where there is no aggregate blending issue between the dense graded and the sand, a geotextile again, 6 inches of cement treated base, and another 10.5 inches of concrete. Notice the 10.5 inches of concrete were kind of consistent through there. I show you a slide here that this is what in 1960s, when we built all the freeways in Michigan, 60s and 70s, this was our pavement section. We had a clay grade with 10 inches of sand on top of that clay that was extended and daylighted at the edge of the slope. That was our drainage. We didn't put under drain piping in. And this section was well drained for 40, 50 years like we're doing today. They laid a 4-inch ag base layer of a fairly clean, denser graded material. Water would go through it, but it was basically a working platform on top of the sand so we could construct the pavements. And recall back in the 60s, many of these pavements were built on forms. That was before we had slip form pavers when a lot of this stuff was started. So there was basically a form platform, and then the paving and mixing operations were actually on the grade during this construction. But then 9 inches of concrete was selected for the standard pavement. Back in the 50s, when they designed a lot of the stuff, they didn't really know how much traffic they would have, so they just built a standard section. But notice, when we raise the grade, we add extra base courses, we make a little bit thicker section, and now we have our under drains that we're relying on nowadays. We've, instead of draining out to the slope, we're putting in under drains. But to get this clearance between the under drain outlet and the bottom of ditch, we're running from a 25-inch section to a 42-inch section. You take 42 inches and add the 2 to 3 feet of freeboard. As you drive around this country, your state, there's probably not a lot of freeways that have 6 to 7 feet of clearance between the bottom of the ditches and the profile grade line of that road. That's a pretty substantial change, and that requires significant more right-of-way, which is almost a deal breaker. And that's why we came back with this section the 30.5-inch concrete section that only had 30.5 inches of material using that stabilization. That really helped us reduce that section, and I think it will really help us reduce our costs long term. On the 30-year design, we had, this was built over in Flint off of 75 and I-69 on the NAFTA route. The standard section was our 10 inches of base on top of the clay grade, 6 inches of these open graded aggregate, and 9.5 inches of concrete pavement. Our 30-year design that we used was we did treat the soil with it, and in fact, it was a cement stabilization. The materials, you know, to stabilize, you can use lime, you can use fly ash, you can use cement. But the soil itself is really the one that should dictate to you which material you should use. Certain more granular materials, lime becomes less effective. The heavy fatty clays, the lime is pretty effective. But those are the kind of decisions that your soil engineer can make. We had 8 inches of the sand base on top of that. We added a dense graded layer, and this really became our working platform. But again, we limited the -200 a little bit, so it wasn't, water could pass through this material. The 6 inches of cement treated, open graded base, and then 10.5 inches of concrete pavement over the top. Our sections were, you know, there's about a 5-inch difference, but it was pretty reasonable. The sections went down well. The crews that built these, in fact, we had one contractor got both of the projects, and their crews report that this section they built was a much more solid feeling. It was a much beefier section. They felt like they were building something pretty strong and solid. On the other hand, when they were building the standard section, they were kind of wondering why they were still paving some days. They just felt that this just didn't feel they just didn't like what they were doing some days. It scared them. And typically in the past, our sections were that if we found some unsuitable, and when I say unsuitable material, it could be some bad material, but most times it's material that's really over too much water in it. Its water has been drawn up to it. You run heavy equipment in a field back and forth over the same spot, you can bring water up pretty easily. And so what they've done in the past is they do a lot of undercut and backfill. And so now what we're doing is when we undercut and backfill, it's important that we add some drainage piping to pick that water up. If we don't put drains in and we put some kind of a granular material back in, we are creating a hugely non-uniform support system for our pavements. And we wonder why after 20 years we start having pavement failures when we've artificially created a non-uniform material that we build our pavements on. The drainage is critical. I know in Ohio and here in Michigan, we do get our share of rain. We're not out west where we have no humidity and no rain. We have lots of rains in our state. In 2016, MDOT had a research project done by Lawrence Tech University. And they were evaluating the stabilization materials. They came up with some conclusions here that I'm sharing with you that, well, let me read them and then I'll share some thoughts. But they said no significant pavement thickness changes were expected using recommended modulus values for stabilized area during pavement designs. I think you've probably seen that in Ohio. You can put all kinds of base material in, and it might change the concrete pavement thickness by a quarter to a half inch. The AASHTO 93 system doesn't seem to recognize base enhancements. They don't put any kind of credit for it. You know, in the HMA section, you get all kinds of credit for it, but not in the concrete designs, and that's a problem. And the ME is pretty similar as far as recognizing values in the base layers. That really doesn't give credit for very much of the base enhancements. But still, then it says, still, the subgrade stabilization will provide a stable, uniform pavement foundation for construction, as well as for the in-service pavement structure. Okay, they're saying the stabilization does some pretty good stuff for us, and it does perform. And they did some in-service pavement checks on some projects we had built, but they're still not. They're saying that designs don't recognize it. And then it goes to say, however, if the properties of the stabilized layers were used for pavement design, so if you changed your pavement section because of the stabilization, it's recommended to have at least 20 inches of cover that's made up of base, subbase, and pavement surface above the stabilized grade. And this is due to the frost action that can happen. That they feel that their history on their field performance, that section of stabilization had to be down at least 20 inches, or the freeze thaw action could break that stabilization down enough that it would no longer be helping the performance of that pavement. And so we've got to be careful as we go forward with this stuff. The other part of the equation for building a long-term pavement is the concrete layer itself. And that's where durability comes in. In Michigan, we've been working for about 15 years now with well-graded aggregates and reduced cement content. Our standard paving mix now, the pavers are usually running with about 500 total pounds of cementitious material. And we're replacing 35% of that cement typically with a supplemental cement. So we are using much less cement. We're using well-graded materials. So we're putting in aggregates, smaller aggregates, replacing some of that cement paste. The cement paste is the weakest part of the concrete. So we are reducing the weak stuff and adding in more aggregate, which is the better quality. So we're using supplemental cements, and we're using those year round, because in 25 years, that concrete doesn't know whether it was built in July or November. We're looking at our air systems. We had to build some better air systems than what we were building in the 90s. And we also are we're changing some of the testing that we're doing on the air systems. We're looking at permeability testing. If we can make our concretes dense so water can't get in, all of the other bad things can't get in, we can make our concrete somewhat waterproof. Curing, because of SCMs, is a critical item, more so than ever. So we're making curing a pay item. And then we'll talk a little bit about dowel bars, but if we're looking at building pavements that will last beyond 50 years, in a 20-year design, probably the corrosion of the dowel bars never becomes an issue. But at some point, the dowel bars are going to become the weak link. We needed to do something to enhance those as well. I took this picture off of another college campus nearby my office here in Lansing. And the caption I put on this thing, snow is coming sometimes. And you can see this path, they were spraying a salt brine on the pathways around campus because they knew it was going to snow in the next couple of days. And you can see how a chloride-based salt brine brings in water from quite a ways away. And it seems like it's always wet. On a sunny day, here's a sidewalk near my office. Look at all the water surrounding the calcium chloride salt pellets. Calcium chloride attracts water. It stays wet. It's great for dust control. That's what you put on your gravel roads, right? Whereas sodium chloride or rock salt, safe salt, it does not attract water. It kind of turns to dust on you once the snow and the moisture leaves. This is the stuff we should be putting on our roads, like the old rock salt. But these new calcium chlorides were some pretty bad actors that we've had to deal with. Jason Weiss, formerly out of Purdue and now out of Oregon State, has done some really good research. And these salt brines are getting into our concretes, and they're reacting with the calcium hydroxide in our concretes. And they're producing a new material called oxychloride material. We put air entrainment in the concrete to protect it from water expansion during its phase change from a liquid to a solid. It can expand about 9 times. Oxychloride expansion potential is 30 times. And then the temperature required for this reaction can be well above 32 degrees. So you don't have to get to 32. It can go through a phase change in the upper 30s. So how many more cycles can we go through in a winter where it doesn't quite get to 32, but we still made a phase change that created a negative reaction? And Will Hansen out of the University of Michigan has done some really good research along with people up in Michigan Tech, Larry Sutter. This picture on the left is a sample that was run through 70 cycles of salt exposure. And these rocks weren't just placed there. They were placed just like they were on this right side. This is a cut sample, but the paste has just been eaten away with 70 cycles. With just a distilled water where we have a decent air system, we got no erosion. But this salt has really been problematic. And that is something that we've had to learn to deal with here. So the hydration reaction, this is just a little quick chemistry, but you put cement plus water, you get CSH, calcium silicate hydroxates, and you get CH, calcium hydroxide. These are glue These are glue, or like stalactites and stalagmites in a cave. Calcium hydroxide is chalk. So we get some really good stuff and we get chalk. During the cement hydration process, you see how these tentacles of calcium silicate hydroxide grow on top of cement particles or aggregate particles. That's what connects everything together. But between all these little particles, that's where the calcium hydroxide settles in and sets up. Calcium hydroxide is leachable. Water can get in and take its calcium hydroxide out, and now we have voids. So the solution is we use the supplemental cements. It could be a fly ash or it could be a slag cement. But cement and water react, like I said before, to get calcium silicate hydroxide and calcium hydroxide. But you add the SCM to it, and it reacts with the calcium hydroxide. It's a secondary reaction, mind you, and you get more of the good stuff. So day 1, you have this reaction. Day 2, you start getting more of the good glue put together. The supplemental cements make more calcium silicate hydroxide, but it consumes the calcium hydroxide, the stuff that is of no value in the mix. The other thing we got to watch in my 25 years of paving concrete taught me this, but we have to watch how we place our materials. The well-graded mixes with SCMs do not need extra water. And the first thing I see crews do when they get a load of concrete is add 10 gallons of water. Many times they don't even look at the stuff before they add the 10 gallons. But with the supplemental cements, we don't need the extra water along with the well-graded materials. They do need to be vibrated though. Water should be added at the plant and not on a grade whenever possible. It's okay maybe to adjust the first truck out of a pour, but by the first round goes through, they ought to be making all the adjustments at the plant. Producers should not hold back water just because the contractor wants to add some on site. We need to get control of that. But because we're using the supplemental cements, and we are using these year round, and by the way, many of our pavers now in the winter or the fall and early spring will bring boilers in and hook them up to their central mix plants, because we want to get the mix temperature up so we can have reasonable saw times. But curing is always essential, but it's even more critical with supplemental cement concrete. That surface of that concrete needs water to hydrate, to make that surface durable. And we need to do that by curing. We keep the water in through the curing process. The other thing we want to look at is the air system. Air content, we've always measured air content and strength, but air content only tells us half the story. The air stability relates to spacing factors. So we need to know the stability or the quality of what kind of air do we have in our concrete. We've been doing in Michigan for the last probably 15 years is measuring the air content of the concrete before the paver for acceptance. But we also take a check on an occasional basis behind the paver. And we look at that delta. How much air loss are we getting going through the paver? If we get more than 1.5% loss through the paver right now in Michigan, we have to stop and figure out what's going on. Most of the pavers will tell you that they're losing about 0.5% to maybe 6/10 behind the paver. But we know with that level of loss, we're getting really good, durable concrete out of it. So we're measuring both the total air content and the stability. A new tool that we're using, and I think you guys probably are doing a little bit of this in Ohio as well, is the super air meter. And that, with one test, tests both the air content and the air quality. And it's using much higher pressures than a standard air meter, so it's got extra clamps. We're finding it's very operator intensive, but its ability to predict are pretty good. We just got to figure out how to record and classify and make sure the test was actually good. We also are looking at permeability, and the test that we're using now is resistivity. You've heard of the chloride ion permeability test with coulombs. You get down below 1,000 coulombs, very low permeability, very hard for water to get in, very hard for all the salts to do damage. We want low permeable concrete. Our standard 6-bag mixes were probably in the range of 4,000 coulombs. The stuff we're making today in Michigan is probably around 1,000 coulombs on our standard paving projects. And by the way, with the reduced cement, our average strength went up 1,000 PSI. So the pavers are averaging about 5,500 PSI with their standard paving mixes at 28 days. Impressive. Curing. You want to start it as soon as the sheen disappears. Complete coverage, but not blotchy. And the finished surface quality is really the critical property we're trying to get at here to make our surfaces durable. One of the things we did with these new projects, these 70-year, 50-year, and 30-year project, is we had a new cure spec, where we are measuring for acceptance the cure application. We're looking at the time of application, 30 minutes or 15 minutes after the shear dissipates. Rate of application. In Michigan, it's 2 coats at 1 gallon per 25 square yards each coat, or 225 square feet per gallon per coat. And And we're also looking at the uniformity of application. Admittedly, the uniformity of application is more of an eye of the beholder. You got to go out there and look at it. Does it look blotchy or does it look pretty uniform? But all three of these are now used. If you're non-compliant, if you're more than 30 minutes behind, it's an automatic suspension of operations until you get back under control. And the engineer can administer $1 per square yard price adjustment to the contractor if they're that far behind. So by measuring it, we are getting a lot more attention paid to it. In my years as a paving superintendent, I would always be the one, I would always go back to see how the cure machine was doing, because everybody was concentrating on dumping the trucks in front of the paver and moving the paver down the road. And it seemed like that the poor person on the cure machine is like the Maytag repairman. He's kind of off by themselves. But by doing this, we've really brought attention to it. And it really has helped us get that cure on quickly. Dowel bars. And I think you've probably got some of the purple dowel bars in Ohio, but typically in the past, everybody used a green epoxy. And what we discovered was, as we looked into this, but the green epoxy was basically developed for rebar when you had to bend it. And so it's a more flexible material, but it doesn't really do well for scratching. It's fine for flexing, but when you are dragging something, it's not the best epoxy. The purple epoxy is an epoxy that was designed to wrap pipes as you they dragged them through installation and seabed floors. It's a much more friction resistant, scratch resistant epoxy. So we made the move to use these purple bars for that. And in addition, we do not coat the ends right now, because really we're worried about this 5 or 6 inch range in the middle of the bar. But if we wanted to upgrade this and coat the ends, it appears that this material will pass many of the same specs required for stainless steel bars as far as long-term performance. So we are looking forward to see how these work. It was a minor incremental change in price, but it was something that we agreed to work on with the department. Future. What are some of the thoughts we had going on some future projects? As I said earlier in the discussion, the left lane of these roads on these freeways don't seem to be the problem. It's always the truck lane, the right lane. And we do think a lot of it is base issues. So one of the ideas we had was, let's trim the subgrade in at least the truck lane at a 3% cross slope. That will assist in getting the water, any water that comes through, to exit the system. 3% will drain better than a 2%. And then keep the base the same, but let the concrete pavement get a little thicker on the edge. This is where the high stress points are with the trucks and everything else. Let's go ahead and let that outside edge be a little thicker. Maybe make this the standard thickness, and build in a little bit of comfort here. Maybe we've been building these freeways, we've always built them the same all the way across. Maybe we could start with a thinner left lane and a thicker right lane. Ways that we can move things forward. With the new grading that we do with total stations, stringless grade control, this is a very simple thing to do in the field. This is something we'll be doing on some future work. Kind of summing it up a little bit, I will tell you the contractors' crews noticed a huge difference between the sections. We now believe, the evidence we've seen that our well-graded SCM mixes are making much more durable concrete. And now the crews are at least feeling that we're building it on a better foundation. We think we have a system here that is going to perform like we anticipate. For a 15% upfront cost, we expect to see a 50% reduction in the future annual cost. That can be a very good thing. And the other thing is the answer almost always involves more than just one thing. We have a tendency to solve one problem and go on when really we have to look at the whole picture anytime we do something new or different. And I got to commend the task force group that MDOT put together, and the projects we picked. We did look holistically at these, and we're looking forward to some nice long-term performance out of these projects. With that, I guess I'll turn it back over to Wayne and see if we have any other questions.
Dan, great job. Appreciate it. We do have some questions, as a matter of fact. Some of these relate back more toward the beginning of your presentation, but we'll go through them here.
Okay.
Is the concrete pavement competitive with the stabilized soil and thicker bases?
Yes. It all depends on I guess I would say in the heavy traffic part of Michigan, we are extremely competitive. In the northern part of the state, we're probably less so competitive, and that's a lot of it as is the designs. But every project that we build in Michigan right now goes through the life cycle. But yes, if we start stabilizing, we need to really look at how to equalize that 15% extra cost. That will be part of our discussions with the department going forward.
So kind of a follow-up to that then, Dan, is that 15%, is that what you're saying is competitive, if you can be within about 15%?
Well, you look at bidding numbers and markets, and there are so many things that go into it that it's hard to make a general assumption. But when we run life cycles, our concrete is pretty competitive. In many cases, we're 15, 20% cheaper than HMA on some of these high volume roads. But I've seen prices change over the last 10 or 12 years where that balance has gotten closer to 50-50 or 0%. You know, they're pretty close, pretty competitive. Right now in Michigan, if we are within 10% on major freeway projects on a life cycle with HMA, then the jobs go to alternate pavement bidding, where the final determination of low life cycle is through the bidding process itself. But commodity prices can change overnight, it seems. But I would say we're relatively very competitive. Let's put it that way.
Okay. Next question. What is the limit to the minus number 200 material in the dense graded base?
The dense graded base is, if we limit it to 5-6% max, it still allows water to get through. You get up to 8 or 9%, it starts plugging it up pretty quick. And that's different. If you're looking at a slag aggregate mix, you may be able to get to 10% minus 200s or the slag aggregate type material that you'd have around Cleveland. But if you're looking at a limestone, 6-7% can probably, those kind of fines can plug it up and make it non-drainable. So 5% or less is probably a good target.
Okay. And the test that you're performing for permeability, what are all the tests you're performing for permeability?
Right now we're using, we do some, the main test is the resistivity test. And that's part of the PEM program that the National CP Tech Center is working on. I think Ohio is part of that session as well.
Okay. You answered the question about the green versus purple on the dowel bars. I think that was handled in your slides. What is your take and experience with fiber mesh products for pavement life and durability?
when we look at thinner overlays, 5 inches or less, we are recommending that they use fibers in those mixes. I haven't seen where fibers are a huge benefit once you get above 6 or 7 inches, 6 inches. It all depends on your joint spacing, but I really see them as very beneficial for the thinner sections for sure.
Okay. What type of reinforcing does Michigan use in your pavements?
Right now, our pavements are non-reinforced. We use about a 14 to 15 foot joint spacing with dowels at the planned joints. The last of the mesh pavements, where we had a mesh reinforcement, were built in around 2002, I think, is when we last stopped using those.
Okay. Another question I got here is the target air percent in Michigan. What do you target for your concrete?
The specification is 5.5 to 8.5. And on all paving jobs, we are under a PWL specification. That is only on the state mainline projects typically. With a target, with a 5.5 to 8.5 band, the recommended target is around 7 to 7.2. If you're in that 7%, 7.2 range, you have a very good likelihood of not going outside of the spec limit. Even with the range of test result, two different testers testing the same concrete, you can have a little difference between meters and between testers, but the smart money is you should target a little over 7%. I guess with the well-graded mixes, our specification for concrete pavers, the pavements, 3,500 PSI concrete. With their old mixes, we were at 4,500 PSI. We are now approaching 5,500 PSI for an average. So we do have, strength is not an issue. So whether you think 6% or 7% air, you're not going to lose enough strength to make any difference. So 7% is a pretty good number for us.
Right. This question just kind of came in as a follow-up. What's your doable SAM numbers for the air test?
The recommendation out of Tyler Lay out of Oklahoma is 0.2 or less. When mixes are running right, we're in that 0.17 to 0.19 range. What we're finding though is a competent tester will accurately, that's run the SAM meter quite a few times, probably gets a right answer out of that machine 6 to 7 times out of 10. But there's about 30% of the time where an air leak or some process issue crops up that you didn't notice, and that test is not a valid test. So the thing we're trying to sort out, and Federal Highway's engaged with it as well, is how do you deal with which test is a good test and which test is not a good test. And Tyler's working on that as well.
Okay. One more question came in. How do you measure strength for acceptance? Are you using cylinders, cores, beams? What's the process for Michigan?
We are using cylinders. And we do have a system where the first 24 hours, the cylinders are stored on the site in a container that is specially designed, whether it's a cooler, but they have to watch the temperature controls on them to maintain between 60 and 80. And then they're transported to the state's lab at 24 to 36 hours type time frame. And then they're tested in compression machines.
What's in the process for that? Would you rate that as going well, Is that a hit and miss? How are they doing with it?
I would tell you that it's actually going pretty good. And what we have done, MCA has for years run a round robin every fall of all the testing labs that would want to participate. And about 6 or 7 years ago, MDOT jumped in with us and they're now participating. So we have every known breaker that breaks for any official word. All the consulting firms, all the MDOT labs, all the labs that do work are part of this round robin. And we just, in fact, they're probably in the process. They're going through the curing right now, but we make up several hundred cylinders in our lab here in Lansing early November. And then and 7 days later, the labs from all over the state come and pick up the cylinders. What we require is any lab that reports a cylinder break that is more than 2 standard deviations out from the rest of the reports, they have to write a corrective action plan to figure out why they're out of compliance with the rest of the state. 2 standard deviations a few years ago was 300 or 400 PSI. Now 2 standard deviations are approaching 100 PSI. So it has really helped the whole industry on the way they report test results and strength results. And the other key is this idea that we protect the cylinders for that first 24 hours, because if we don't have good control of the curing environment of the cylinders, especially in the first 24 hours, then all bets are off on 28-day strengths. But we have a pretty good handle on it. It's very rare that we hear about a cylinder nowadays that doesn't meet the strength requirements. We do use some beams for open to traffic strength, but not for pavement.
All right, last question, I promise you. Pay factor deduction based on high standards, or excuse me, on the high standard deviations. Is there any type of deduction?
Yeah, that's our PWL. We do have a percent within limit that it covers the paving mixtures for the paving jobs. I guess that's as much as I could say on that. But one air test that's out a little bit can really can take somebody out of incentive or put them in penalty pretty easily. So there's a heavy amount of attention paid to the testing during the day and the control of the cylinders.
All right, Dan, thank you very much. Great presentation. Great job answering questions. Really appreciate your time. Again, for the group, before we log off here, reminder that next week we're meeting on Tuesday at 1:30. Mr. Dean Kraft will be talking about specification and strategies to eliminate concrete moisture. This will be number 6 in our series of 7. So thanks again, Dan, and appreciate it. Everybody have a good day.